maybe this 100-year period is the period that had the great capitalistic outcome, and from here on out, particle physics is not going to produce anything that someone can monetize. We should not stop it, even if that's the case, because we are humans who want to know things, and
Right.
and making sure that we give people the capacity, the time, the resources, the space to actually pursue those questions kind of on behalf of humanity. That sounds very grand.
No, it's
but
true.
giving people that capacity is such an important thing.
Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to what promises to be one of the nerdiest episodes of the year. And that's when two experimental physicists get to just seriously nerd out over our favorite subject, which is building coolest stuff in the universe and using it to learn hitherto unknown things. And that's Professor Suzie Sheehy of the University of Melbourne, I think is correct pronunciation, and Oxford on occasion, as I understand it. You're the 10th Oxonian to be on. I think you're the first Melbourneian to be on, but I don't know.
Yay.
You're the second Australian to be on. We had Luke Barnes on recently this year, already in 2023. But today it is because of a phenomenal book that I've been waiting and asking you to come on the podcast for over a year, because I mistakenly thought it was already out in America, but it actually came out in the UK first, and that's called The Matter of Everything. And that will be the subject of today's conversation. And Suzie, as you know, because I just told you, on this podcast, we love to do the thing you're never supposed to do, which is to judge a book by its cover. But I always say, what else do you have to go on? You don't. Every book doesn't come with a crystal ball that you can look into. So tell us.
It's a particularly pretty cover, this one
as
well.
It is beautiful, evocative, and so we love to understand the title and the cover art, but especially the subtitles, because usually sometimes the author doesn't have control over almost anything but the subtitles. So tell me, Professor, how did you come up with the name, the title, the graphics? What did you use as inspiration for this wonderful new book?
Yeah, so as you just said, this is actually the second release, so it's already out in the UK and Commonwealth, which actually had a different cover and a different subtitle. So that's an interesting change. So the contribution of the main title, The Matter of Everything, was mine and actually my literary agents. We came up with that together, and I just, as soon as we hit on it, it was like, oh yeah, it has to be that, because it's sort of a double meaning, right? So it's literally a book about matter, and matter literally makes up everything. And at the same time, it's sort of talking about the matter of everything, which implies sort of all of the stuff in our world, including technologies and modern society, which the book also hits on. So that kind of worked well. The original subtitle for the UK version is called 12 Experiments That Changed Our World. And actually, a lot of people prefer the new US-Canada subtitle, which is How Curiosity, Physics, and Improbable Experiments Change the World. I think it's just a little bit more descriptive of what's actually in the book, and the fact it is a story about experiments and particle physics.
Very good. So this book covers these 12 phenomenal, kind of world and universe changing experiments. But the picture on the cover, at least the one you're holding now, is not of a modern experiment, right? Unless I miss some serious symbolism there.
No, it's just, I mean, I think it's beautiful, this pattern of just the electric fields around there's a positive charge and negative charge. It's just the electric field lines sort of displaying the invisible forces of nature. And I think that was a lovely way. That was the first cover art they proposed to me for the US version, and everyone loved it. People have pointed out some other slightly controversial things about the cover, which I also love, and I wonder if that's something that you have picked up on.
No, tell us, Suzie, please.
So you notice the colorway is really beautiful. I love it, and there's a pink. So a couple of people have pointed out, and you can cut this from the podcast if it's too much, a couple of people have pointed out a Georgia O'Keeffe-esque element of the pattern.
Those dirty-minded physicists, come on.
And you know what? As soon as someone pointed that out to me, I was like, oh, this is definitely the cover for me then, as a female physicist working in a male-dominated field. And
a
all throughout the book,
self-declared feminist, right?
exactly. And all throughout the book, I've tried to reintegrate the stories of women whose stories are normally left out of the history of physics. And so the fact that there is like a subtle feminist angle to the cover, just, nailed it.
Yeah, that's great. That's right. Although we have to be careful with our metaphors and so forth here. I thought it had something to do, as a feminist, I thought it had to do with you creating, what could be called, I believe there's third wave feminism, if I've gotten that right. But you are the unique person on Earth, perhaps, to coin, particle wave feminism. I think you could make that duality better than anybody on Earth.
Particle wave duality feminism, for sure. Let's do it.
And
you can be in there with me.
That's right. You talk about that in this very book. You talk about the mysterious world of quantum and how it was revolutionized and how we made the transition. And just, people think, all these discoveries are hundreds of years old. No, the experiments you talk about are some of which occurred in the last 10 years. And obviously you cover the Higgs. We've covered that a lot. And you do sing the praises, rightfully so, of many of the great heroines of modern science, not just physics. I was just listening to an interview I did with Ashley Yeager a year or so ago about Vera Rubin, who is a Titanic scientist, worked here at UC San Diego with Jeffrey and Margaret Burbage. And Margaret was one of the Titanic physicists of the 20th century, astronomers of all time, perhaps. And I wonder if we could start with the first dichotomy that is sometimes lost on the general public. When I go on podcasts, or sometimes I'm sure you've been on podcasts, people think of physicists as all the same. First of all, we're all, Brian Greene or Jana Levin or what have you. But what is the primary distinction in your mind of an experimental physicist? What can he or she most uniquely contribute to the public's understanding of science?
Yeah, so I thought that was an interesting one, that when I started talking to people about physics, and even when they knew I was a physicist, they just kind of assumed that I'm a theoretical physicist. And that, we can sort of blame a little bit the fact that in popular culture, a lot of physics is presented that way. A lot of books are written by theoretical physicists, maybe because they're the ones who have the time to sit down and write while the rest of us are in the lab. But in my view, there's sort of, if we were to create that dichotomy between theorists and experimentalists, some people do both, but an experimental physicist, rather than just looking at the mathematics and the mathematical concepts and trying to create a theory from which something can be predicted, their job, I sort of say, is much more nuanced. So they have to keep in mind and understand the mathematics and the theory and work with it, but they also have to be able to look beyond it and to look for things that maybe nobody has ever thought about before and nobody has predicted. And they also have a very unique skill set. So as well as having the mathematical and theoretical background and training, as you know, we also have to have all these other skills, which you often only learn on the job. Things like electronics, superconductivity, and working with like cryogenics, things like back in the day it would have been glass blowing. Budgets. Yeah. Oh my goodness. Bane of my existence. Being able to just design, sort of almost verging on engineering and being able to understand how to get something precision engineered, understanding grounding loops in the lab, understanding radiation shielding. That's been my one lately, building my new lab. So there's all these different skills that we actually have to have, as well as signal processing, etc. Just to get to the point of doing something which can create new knowledge. And yet, when you combine all those skills together, we're able to do something that, in my view, a theorist can't, which is we can find something which we never thought was out there. And that's a really powerful skill.
And it kind of dovetails into my next question, which is, do we need more Diracks or do we need more Rutherfords? They're both big figures in this book. But, are we overinvested? We've had a lot of contrarians on this podcast, ranging from Sabina Hassenfelder to Neil Turok, decrying the stagnation in theoretical physics. Essentially, for those that may not have heard those many interviews, there's a sense that string theory has kind of sucked all the oxygen out of the theoretical particle physics world, and therefore there's not really room or oxygen molecules left for alternative theories, A. But B, we're kind of beholden to this unification dream that last bore fruit perhaps in the late 1970s. What's your take? Do you feel like we're underinvested in theory, overinvested, regardless of the branch of theory, whether it's particle physics or whatever. Do you think if you were, queen of the earth and you had control over the purse strings, not just over Australian purse strings, but what would you invest in? What would be, obviously you'd want some of both, but what do you think is the most fruitful avenue for us to pick the high hanging fruit that remains?
Yeah, I think obviously we need both, right? And I think I'd have to go through the numbers for each individual country for like how well we're investing in each of those different areas. Although I do agree with the idea that we often sort of jump on a bandwagon to the expense of other sort of lesser researched areas. And even the way that our funding systems sometimes work is that unless you're working in that hot area, you basically won't get any money. And money, as gosh as it is to mention it alongside curiosity-driven research, money is what gets things done. So that is an important perspective. I think, in my view, and one of the things I've tried to really champion in this book is just the power of experiments, full stop. Now, you can think on many different scales with this. Particle physics is at a point where our future experiments on the large scale are absolutely freaking enormous, right? And are going to consume vast amounts of budget to build any sort of future collider or large experiment. There, tens of billions of dollars, thousands of people, etc. So that is a huge investment. And I do think we need to be careful about how we make that investment and not commit to something too soon that turns out to be not the thing we really wanted. And that is exactly the process that's happening at the moment. And we have international processes to decide that among the community. And of course, there's always going to be people who are like, oh no, this is completely wrong. You're barking up the wrong tree. But I think as much as we are, as physicists, susceptible to things like groupthink and ego and bias, I think when you've got that many smart people who manage to actually collaborate and agree on what they do want to build together, I think in a way you should go with that, but not at the expense of everything else. So if you're not involved in that like hot big experiment, and actually my confession is in my career, I've never chosen to be on that big experiment. So I only worked on the Large Hadron Collider experiments as an undergraduate, and after that I've worked on other projects, and nowadays I design particle accelerators for medicine. So I sort of stepped away from those big projects because I just decided that wasn't personally how I wanted to work. So I have a massive respect for people who do the same and who go, actually, do you know what? I can do this clever little experiment in my lab, or in my country, I can build this dark matter detector, for example, is one that is being built near me in Melbourne in Australia to do a southern hemisphere version of the Dharma measurement that was made in the northern hemisphere to try and confirm a seasonal variation of dark matter, which would be important if we can do that in the southern hemisphere. So I respect people doing small scale experiments as well. I think in a way, my view is where people appear to have gone wrong, and I am slightly an outsider here because I work on accelerators, not directly on particle physics. My view of where some people go wrong is they really get into their own sort of groupthink and bias. And we are, I like to say that even though science is objective, scientists are not, right? So we do fall into these
That's the problem. Science
patterns.
is done by scientists.
Yeah, if only we could do it with robots. No.
Soon.
Hey friends, just a quick request while you're enjoying this video to leave a thumbs up. My thumb's a little bit preoccupied with all Carl Sagan over here, but I hope yours is free enough to leave a like. It really helps me with the algorithm. And for extra credit homework assignment, leave a comment down below what you're enjoying about this video.
Can I speak to you
So I think I do really appreciate the dissenters, the dissenting voices, and I think they have something valuable to offer, even if those dissenting voices are often like, no, everyone else in the world is wrong and I'm right. But it's worth listening to their arguments,
Right. I'm sure you get those emails. I get them all the time. Professor Keating, I have this great idea, but everyone says I'm crazy. But, they said this guy, Albert, was crazy too. And I just need the help with the math. And then if you help me, I'll split the Nobel Prize. I'll keep the money. You could. But the point, I guess, in right now we're in winter. You're in the middle of summer. We're in graduate student recruiting. So we've got graduate students. I was just on the phone with a brilliant person. No, I won't tell you his name because you might poach him and he might want to move down there. And then I'm trying
Australia's great. Come on over.
Give me the elevator pitch for why a student should want to do experimental physics generally, but in particular to work with Professor Sheehy on particle adjacent, but certainly I have to imagine anyone who's working with you is going to learn a lot about the history, the background, the experimental methods. What's so cool about that? Why is that such a fun thing to do in this age of, kind of reverence for, just content creation on the internet and YouTube, TikTok videos? What is the kind of sine qua non that would attract a brilliant young graduate student to join your lab, as opposed to become a theorist or go into work for Google?
Yeah, really great question. So I think what attracts people, and I'm going off the experience of people who've come and joined my group here, right? And I ask them usually like, yeah, what attracted you to come and work in this area? And it was kind of exactly the same that attracted me to the area of particle accelerators themselves and the instrumentation and the experimental side, which is that all of these big ideas are amazing. All of these big ideas of how our universe works and that theoretical and conceptual understanding. But at the end of the day, unless you're in the arena, unless you're in there and actually building something and trying to do it in a hands-on way, you're sort of missing in a way the fun of it. And we live in this age where so much of our technology is like black box invisible to us. If you can even code, you're like one step ahead. But to be able to actually build something with your own hands that lets you experience the world in a way that you otherwise can't see and experience. And then the added bonus in my group is to then do something with that knowledge, go back to the drawing board and design instruments and experiments which can actually make a difference to people's lives in the real world, as well as make a difference potentially to the next generation of hadron colliders or particle physics experiments. That potentiality of, you come work in my lab, you're going to learn the skills that can do so many things in the world, whether you're interested in that practical everyday application of, extending cancer care access to low and middle income countries, which is one of the projects I work on, or whether you want to work toward the future circular collider at CERN. That's one of the things that I find amazing in my field about accelerator physics, is that we mix together all these different areas of like plasma physics, nonlinear dynamics, and electromagnetism. And out of that just comes this amazing growth of opportunity of what we can do in the world using the fundamental nature of matter. I think that's my that would be my elevator pitch, and it's what people
that's
sort of
a strong
reflected
pitch,
back
and
to
then
me.
you could just hit them with the book and say, you're an idiot.
Yeah, and here's a signed copy. Join the group. Yeah.
I make them pay. I make all prospective graduates pay. No, I'm just kidding. So when I first heard about your book, I thought, it might be kind of a counterpoint to Hope Yaron has this book called Lab Girl, which is a lovely book. She's a biologist, a tree biologist, ecologist, I think. I think she was at Hawaii, but now she's in Anyway, I can't keep track of all these people.
Yeah, I've read her book. Yeah.
Yeah, it was interesting because I think the issue of, her personal struggles are interesting, and certainly almost everything is memoir. But what I love so much about your book is that it's personal, and you talk about, but you're talking about it from the perspective of a professional. And what the hallmark is of the book is that you're kind of entreating the reader to approach these incredibly mysterious phenomena as a professional, not just like an interested dilettante. And I wonder, was that a conscious choice? Did you want to, take people less on a memoir kind of journey as Hope did, which is a wonderful book, and I love it, and I've given it to as gifts, but was it less intended to be a memoir so that you could focus on that which drew you to become an experimental physicist?
Yeah, I think at first, when I first started writing it, it's my first book, right? It's my debut. So at first you don't know how to write a book, right?
Yeah.
And working through that exact question was part of the process of writing the book, is how much of me, how much of my stories do I want in the book versus how much of this is about the ideas that excite me and trying to portray those ideas. And eventually there was a sort of compromise made of where sort of my story leads us in and my story sort of takes us out again at the end and brings us back to today. But then within the book, I chose to sort of lead with the science and lead with that curiosity and lead with those outcomes. But I mentioned before that I rewrote in these stories of women. And I think one of the wonderful things about doing that, I realized when we sort of stepped back from the process and read the finished thing, is that their stories kind of tell my story in a way without me having to spell out all the ins and outs in a memoir. And what's interesting is that my US editor, it was actually the same editor who did Hope Jaron's Lab Girl.
Oh, really?
Yeah. So we talked a lot about that and about how much to include. It was also I had a UK editor and a US editor, so there's always that play in the publishing world of, well, it's my decision at the end of the day, and they actually had differing opinions on how much should be memoir and how much should be really science led. And I'm really pleased with how it balanced out in the end, because I don't have to sit through every interview with people asking me about every incidence of, say, harassment that I've experienced, because it's not in there.
Right.
But at the same time, I get to highlight the women who really did the work, and that just feels so much more positive and empowering to me to be able to bring that story instead of like a negative story about their experience or my experience.
Yeah. I mean, one of the most towering figures, and, I've done a video on my channel about it, I called the most important experiment of all time, was Madame Wu, C.S. Wu, talk in the book about. I wonder if you could pick a favorite. All of us who have children always say, we can't choose our favorite child. My mom used to say it's like asking her to choose between her left arm and her right arm. To which I'd say, Mom, you're left-handed. Come on, you're obviously going to choose your left hand. But is there a person, male or female, it doesn't matter, but is there a character? Is there a figure that really stands out? I mean, the one that keeps coming back so often is Rutherford, and he just seemed to have this brought to life by your wonderful writing, this outsized personality, which I never knew about. I mean, I remember seeing him on the way to Antarctica. We go through, there's a museum, and there's a lot of information about him, and then I know he was in Canada and so forth. But he initiated so much of what we do as modern particle physics. He was kind of my favorite, if I have to confess, character in the book. But do you have a favorite? Is there a figure who really brought the drama, the passion, the love that you and I share for doing experiments to life most for you?
I feel like that description is really describing Ernest Rutherford and his approach, and it becomes more difficult in the second half of the book when we go past World War II and then we get these large collaborations and international experiments, because then it becomes less about the individual and more about the collaboration. So it becomes difficult then to just sort of say, oh yeah, this amazing person from this era. If I had to choose someone other than Rutherford, it would be Bob Wilson, who was actually the founding director of what became Fermilab, because he was this beautiful combination of experimental physicist, kind of cowboy, and poet and sculptor. So he had this wonderful combination of skills in the creative, the practical, and the theoretical, which he sort of brought to bear in his leadership of that project. And his quote, which I write in the book, justifying the sort of Fermilab project to Congress, is one that I use so much in so many of my talks, because it so epitomizes why we do particle physics. Do you want me to read out just the end of it, if I can find it?
Yeah, I would love that. Yeah.
Yeah, let's see if I can find it.
It is so poetic, and it actually, I heard it spoken by Leon Letterman at my college graduation. Leon was, of course, a towering figure in particle physics, Nobel laureate, and he quoted from this at the commencement speech at Case Western, where I went 30 years ago. So, yeah, I would love it if you have it handy. Otherwise, we'll make sure to put it on screen.
Sorry. Yeah, so Wilson was before the Senator, John Pasteur, who was asking him about this proposed machine, and it was 1969. And, obviously it's costly and it's risky because they don't know what's going to come of it, because it's doing research, obviously. And so at first, Wilson actually justifies it based on, well, we're doing extremely difficult technical things, and the outcome of that always sort of pays for itself in the long run in new technological innovations, which became true with the Tevatron, because they basically industrialized superconducting wire. So that's why we now have MRI scanners available. But then Wilson really delves down on the cultural aspect. So the senator asks him, does this project have anything to do with the security of the country? And Wilson just says no. So he was involved in the Manhattan Project. He's a pacifist, very strong pacifist at this point. And he will have nothing to do with defense and ever again. So the senator pushes him on it. It's like, nothing at all. He's trying to help him justify it. And then Wilson just knocks it out the park. He says, it has only to do with the respect with which we regard one another, the dignity of man, our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things we really venerate in this country and are patriotic about. It has nothing to do directly with defending our country, except to make it worth defending.
No.
And every time I get shivers, every time.
It's so evocative and so true. It's my late great colleague, particle physicist Hans Parr, who passed away sadly a few years ago. He was Letterman's graduate student, actually. And he used to say things, in his German accent, that relativity is the highest culmination of Western civilization. I say, Western civilization? What about the Mona Lisa? But if you think about it, really, I would only add experimental verification of relativity, because relativity required mathematics, advanced communication, and then finally verification and scientific hypothesis testing by experiments. And we take it for granted every day anytime we use, a GPS device to get anywhere. But I wonder, when we're teaching these things, because the Einsteins, I have all these I've got Carl Sagan around here somewhere. I've got Isaac Newton. I've got Einstein, but I don't have any experimentalists. Maybe someday I'll be a finger puppet of Suzie Sheehy. But I don't know if you'd license your likeness. But the feeling I have is I want my students to know as much about theory as any of the theoretical graduate students studying theoretical physics. I just don't expect them to do theoretical physics, like come up with some new theory, although some have, come up with contributions to phenomenology or perhaps some analysis technology. But what do you think is we've heard from Lenny Susskind, another famous, ultra-famous theoretical physicist, the theoretical minimum. What's the experimental minimum? Is it this book? Because the book is certainly would be a component of it if I had to, come up with a curriculum for bright undergraduates to kind of what's the next, how do we become an experimental physicist? But what about before this book takes place? Every author has to start the narrative somewhere. Why did you draw the line at the 20th century and beyond?
Oh goodness! So the choice of the time scale to explain is not the whole story of experimental physics. In fact, it arguably ignores thousands of experiments that could have been beautiful, right? There's many versions of this book that could have been written. So, choose your own adventure. But I chose the particle physics route, partly because that's my background, but also because particle physics just has this reputation of being like such an esoteric subject, right? Such a theoretical subject, even quantum mechanics, the development of that happens somewhat within the book. Nuclear physics, you say the word nuclear, everyone just has this very negative connotation. Radiation has a similar connotation. And then by the time you get to quarks, everyone's like, who cares? It's not real, So there's this view that the different things that I talk about in particle physics, people have a very disjointed view of them. And they also have this view that they're very separate from our lives. And I just had this very strong feeling from working in the field for so long that wait, no, this stuff underpins our technology. And we don't even know, most people don't even know that it's there because they think that physics is just a theoretical subject and that it doesn't have ramifications in the real world when you think about things like how fundamental particles work. And so that was my key thing that I wanted to get across, was that this stuff really affects your lives. It may affect it on a long time scale because of the innovations that come from it. It may affect it on the short term because, suddenly you understand there's radiation raining down on you from space and that affects things. So I wanted people to put those things together, and I found that the way to put those things together was really through the experiments, through that development and the discoveries that were made, not through the theoretical angle, in my opinion. But you mentioned something early in the formation of that question about teaching. And that's like a whole other can of worms because, we teach theoretical physics. Basically, any course you take in physics is almost entirely theoretical physics.
Right.
And I agree with you that I want my students coming into the lab being able to solve Hamiltonians and being able to, do theoretical physics. They actually need it to do their experimental work as well. But then where are they going to get these experimental skills from? And some students are lucky enough that they went to a high school or, that they have great laboratory, undergraduate laboratories available to them in their universities, and some don't. And I was someone who really didn't do that much in a hands-on sense when I was in school in science class, but I did do quite a lot sort of out of school in like side projects. And then in university, I was quite lucky that we have like this amazing suite of live demonstrations for lecturers to use, which I now get to demonstrate, which is awesome. And they also have like really good undergraduate laboratory projects here. But even then, there's this point at which you have to learn to go beyond what's written on the like lab script and actually learn to tinker and learn to find your way through a problem, building a thing yourself. And that just at the moment comes from experience. And I do wonder if there's a better way in constructing the way that we teach and talk about physics that would help people, get into that a little bit more, because it's such an important skill. And as we get more and more of our technology, as I said earlier, starts to look like it's a black box and we don't understand what's inside it, we become so divorced from that it's like, well, how many people actually have those skills? Like, are we just going to machine learn everything because we've forgotten how to actually do anything?
That's right. When I have a list of, possible skills wanted, to join my group, I always include like, did your mother own a welding company? Because they won't put those, if I don't know Python, or if I don't know, machine learning, TensorFlow, I can't be a physicist. It's like nothing could really be further from the truth. Even Einstein had some patents, and actually the things that he was most kind of driven by, his Gedanken experiments, were things like that involved the observation of physical phenomena in an experimental context, a magnet, a compass, and the interaction between them that he called Something Deeply Hidden, title of book by past guest Sean Carroll. Or his famous, thoughts on the equivalence principle and the general principle of general relativity, that an observer in free fall would experience no gravitational force, and that he obtained by thinking about it, and he called that his happiest thought. And I always say, like, to what extent could a computer A know what it's like to free fall, and then B, like, what would it mean that it has a happy thought? So I don't think we're going to be replaced anytime soon by any sort of stretch of the imagination.
That's true. But those observational skills are interesting, aren't they? When people come in to do experimental physics, they're like, oh, I've got all these coding skills. And I'm like, okay, so are you cool with getting your crane license? Because you're going to need that in the lab.
And that dovetails next into my question. Like the books, you mentioned that, for theory, it's summed up, there's a progression. You read Jackson, you read Griffith, whatever it is. And then you move up the ladder. Barbara Ryden, past guest on the podcast, the most influential cosmology book in the world right now for undergraduates. And it's all these just series of just like home run after home run, and to the cricket century. Am I getting that right? Cricket century. Is cricket popular down where you are?
It is.
Rugby?
It is.
Okay.
The tennis is on at the moment, so I don't know. Is there a tennis analogy?
That's right. Okay. Ace. I'll say.
There you go.
Ace,
An ace. Yeah.
So it's just one after another, and then to the extent you're right that we teach experiments, it's canned experiments, black box experiments, some from 200 years ago, and then of course you start with the balls rolling down inclined planes, and then we wonder like why aren't students interested in this? But I wonder, my impression of being an experimental physicist for the last 30 plus years is that getting like the answer, whatever that number is like not even half the battle. And most of what we do, correct me if I'm wrong in your field, is looking at the ways that you could be wrong. In other words, the thing we don't teach the students, like we do the Davison-Germer experiment, we do cloud chamber stuff, all the stuff, cool, fun, amazing, things that you describe in your book, right? We do all those. And if you don't get the right answer, if you do like the Cavendish experiment and you get the wrong answer, as I did many times in my undergraduate career, it's because of you. It's not because of the universe, right? So we're taught to get the answer, 6 times 10 to the minus, whatever, for Newton's capital G or whatever it is, or the Millikan oil drop experiment that you also talk about. Now, my problem is that you know that where the answer is. So half the fun of being a physicist is when you don't know what the answer is. You don't even know what you're looking for. And then you have to prove to yourself that you are not, it's not like it being in a court of law. You have to prove that you're right, not that you could be possibly wrong. So I wonder if we don't really do the greatest job teaching students, that the challenge are in the systematic errors and the analysis of what's wrong with the system. And I wonder, to what extent does that drive what you do? And maybe you could explain what is the proper way to think about what we actually do as experimentalists? Is it getting the right answer? Is it assessing the error bars, the tolerances, the bounds? You do this so well as a particle physicist, but what is it to you? What is the as I say, the sine qua non, the core essence of being an experimentalist?
Yeah, I think in some of that explanation there in the question, you actually summed it up pretty well in my experience and opinion, which is that you're trying to build something which is accessing an idea or accessing something in nature that you don't know the answer to. And that was actually the point in my undergraduate career when I decided and got more serious about physics. Is first I got sort of inspired of like what I could learn, but then later I realized I was much more interested in the questions that didn't have answers than the questions that did have answers. And it took me a while to come to that, because everything I was being taught seemed like we already knew the answers, and it was my job to catch up and find out and learn. And if I didn't do that well enough, then I wasn't smart enough because I wasn't Einstein, etc. All the things that we experience as a student when we and yet no one tells you that actually being able to ask good questions is a key skill of being a scientist, and then having the persistence to try and see through your own biases and mistakes and frustrations, especially in the lab, to convince yourself that you have found the answer to your question, because even how you form the question and the many small questions that generates is important. And so a lot of people come into, say, a PhD in one of my labs. I still have a lab over in the UK as well. And they think they're going to be like walking in there, taking some data, doing some fancy new thing, and then
nature, right?
And then actually they're like, oh, why does the signal look this way, and how do I get rid of the noise on this signal, and this experiment appears to have gremlins inside it appears to have a life of its own, why is it not working the way that I think it works?
Professor Sheehy is around, it suddenly stops working.
And there was two wonderful things I found in my research for the book from famous experimentalists, both Ernest Rutherford and J.J. Thomson. And the one about Ernest Rutherford I love, which is that he firmly believed that the more you swear at an experiment, the more likely it is to work. Which maybe only works in the sort of Aussie context, but
right.
I don't typically swear at my experiments. But if you find me doing it, I'm using Rutherford's technique. It's validated.
Channeling Rutherford, yeah.
I mean, it worked for him clearly. But the other thing I found, and I didn't write so much about this in the book, but I read a lot of the autobiographies and memoirs of the experimentalist whose experiments I was writing about. And J.J. Thomson's one was particularly interesting because even to his peers, he was this like super brainy, slightly scarily smart guy, right? And yet in his reflections on working in the lab, he was very open with this sense of frustration and this sense of having to learn your equipment and having to learn your apparatus so much better than you think you're going to need to know about it in order to make any progress in the lab. To the extent that he wrote something, I can't remember the exact quote, but it was something along the lines of that when you have these things that we already know, like you were just talking about, these theoretical ideas, and you're trying to reproduce it, he was like, the least likely place you're going to do that is in the physics lab, because it's just so hard to get those results out in the first place. And this was really my aim in writing the story in the way that I did, is to try and put people in that mindset of what did we actually know at this point in time. And that was very difficult in the research process because everyone writes the physics history backwards from what we know now. And I tried to write it forwards. I was like, what did they actually know at this point in time? What were the questions they were actually asking? And then how did it happen that they got from there to the knowledge that they came to? And I think that digs into the essence of really what we do as experimentalists, which is we are moving knowledge forward, but it does not happen in the linear way that we're taught, the sort of pigeon version of history of physics when we learn the subject. So I hope that that's something people can really take away from the story, is all that work that I put in trying to find the forwards path through the history. Yeah.
It really shines through in the book. And another thing for me, it's like, and I'm sure you've had this experience, too, where you're reading a book by a colleague. It's a popular science or trade book, as they call them here. And you're like, well, I kind of know all this, so I can just skip it. And I should say I read the book, but I also listened to it on audiobook, and Suzie narrates the audio. And it's just, it's mellifluous and lovely, and it is a work to be savored. I really did appreciate it so much. And I want to say, you probably left a lot on the cutting room floor, as you just mentioned. But one of the things that I didn't skip over, and I was like, a nagging thing that always bothered me that you helped to resolve in my mind, which is related to what we do as cosmologists using the cosmic microwave background radiation. One of your colleagues, Christian Reichardt in Melbourne, he and I and our teams are working to investigate and measure the properties and the mass, in fact, of the only elementary particle whose mass is currently unknown, and that's the neutrino. And I always thought to myself, let's say we cosmologists, we're so smart, we've measured the geometry of the universe, the age of the universe, the expansion rate, we're so brilliant. But would a particle physicist really believe an experimentalist in cosmology if, he or she is told that we have measured the mass of a particle? Because that's their domain, right? We're stay in your lane, Keating. But I didn't really appreciate how much the humble cosmic ray played a role, and not just for the phenomenon itself, but I wonder if you could wax poetically about the technology that it enabled and the literal heights that experimentalists went to, as you describe in this wonderful book.
Yeah, I love the story of cosmic rays because it just breaks open our concept of what exists in the universe. Like before the discovery of cosmic rays, I guess people looked out at the night sky and it sort of thought, oh, it's all quiet, and then there's some shiny things off in the distance, And the way it was found, most people don't know what motivated people to go and look for this radiation that comes down from space. And it was that they were in the lab. Sorry, one second. So scientists in the lab in really the early 1900s they just discovered radioactivity. And so the way you measured radioactivity at that point was using an electroscope or an electrometer, which is literally just a really simple device that counts electric charge, or that can tell you how much electric charge there is. And when you move an electroscope away from a radioactive substance, the amount of charge you should pick up should decrease. This 1/r² law, right? And they found that actually, even when it was far away, they seemed to detect more radiation than they expected. And this was something that had plagued them for many years, and it was very difficult because that was the only thing they had to measure it with. So people started getting curious about this. Why is there this extra radiation? Well, radiation itself had been found in minerals from the Earth. So they thought, there just must be more radiation in the Earth in my particular area. So people started taking these things down underwater in submarines. They took them up the Eiffel Tower, and they took them even in tunnels so that they could be surrounded by the Earth. And consistently they found that no, actually it doesn't look like this extra radiation is coming from the Earth. It wasn't consistent. And so then a few people got this idea, we're going to take them up in hot air balloons. We're going to go up further away from the Earth, and then the amount of radiation we discover should decrease. And but the instruments weren't good enough. And then a new version was invented, and finally Victor Hess in about 1911 gets this hot air balloon, does 5 or 6 different flights up to about 5,000 feet, which must have been freezing. I don't know how he operated the instruments at that height, but he managed to do the first sort of definitive set of measurements that showed that first the radiation decreases as you go away from the Earth, from the minerals, and then the amount of radiation that he detected increased and increased further and further as he went up. And this, he concluded, was radiation coming from space, interacting in the atmosphere, and then creating whatever it was that he was detecting. And he had no idea what it was composed of at that point. And then, almost coincidentally at the same time, one of the researchers who'd gone in a tunnel in Scotland to try and solve this radiation problem, but wasn't that interested in it, Charles Wilson, he invents the first type of particle detector called a cloud chamber, which he originally invented to study meteorology, and then discovered that little bits of radiation would cause particle tracks that went through this beautiful sort of alcohol vapor or water vapor he used originally in his chamber. And so people start taking these cloud chambers up mountains. It was this incredibly adventurous period through to the early mid 1930s, where you get these these chambers with their photographic devices wrapped in these huge coils that form a magnet that sort of consumes all the electricity from a huge generator. And, the truck breaks down on the way up the mountain and it's freezing, and they spend like 6 weeks collecting data. And then in 1932, they found in the images from a cloud chamber particles that looked like electrons but were bending the wrong way in a magnetic field, which almost immediately they realized were positrons, which the first discovered form of antimatter. But Carl Anderson, who did that experiment, didn't even know that antimatter had been predicted 3 years earlier by Dirac. He found it in the experiment without knowing it was predicted. And Dirac didn't motivate anybody to go out and do the experiment because he didn't think it was really real in nature. Right. He thought it was almost like a quirk of the equations. Right. So we get antimatter, and then 4 years later we also get the discovery of the muon that no one predicted at all, which is the heavier version of the electron. And from there, really, we start to get this sense of, there is much more richness and complexity to matter. I put in inverted commas because most people think of matter as the stuff in front of us, but muons and positrons are not in atoms. And suddenly it opens up this exploration of the subatomic world. And it blows my mind that we've even found uses for those particles. So muons, because they travel through rock, they can travel through large amounts of rock. You can use them to image the inside of a pyramid they found a new empty chamber in Khufu's Great Pyramid in Giza that way. You can even use them to image magma inside a volcano just by putting detectors either side and using the cosmic ray muons. And then positrons are amazing because you can use radioisotopes that emit positrons inside the human body to trace out the functions of the human body using positron emission tomography scanners. So again, like linking up, people went out and found these things almost serendipitously. Even the instruments were invented almost serendipitously. And then today, if I need my thyroid scanned, I go in the hospital and I just don't think twice about it, there's a scanner there. Well, look at the backstory of that scanner. It's absolutely incredible.
Yeah, it truly is. And actually, I want to talk more about serendipity in the time we have left. But first, I want to talk more about your actual work and what you're doing now in medical and device physics. And just to remind listeners, we're talking with Professor Suzie Sheehy, author of The Matter of Everything. And I shouldn't show you, one of my kids has a T-shirt that he got from one of his friends, and it said, you matter on the front of it. And it says, unless you multiply by c squared, then you energy. And I got so mad at that shirt because it's like, no, it's not matter, it's mass, come on. But anyway, you can't correct what these T-shirt manufacturers are doing nowadays. But we're talking with Suzie, author of The Matter of Everything. Now, the kind of pivot that takes place in this book, at least for you professionally, is that, spoiler alert, you kind of win the day, the heroine's journey. She's now a professor, the coveted, goal of science. And maybe if we get a chance to talk some other time, maybe here or there, we'll get into more of what I call the academic Hunger Games and how hard it is and how just impressive you are and how much stuff you've done to get where you are. But talk about what you do. What is the science that you're involved with, the application ranging from what Alfred Nobel really wanted with his Nobel Prizes, as I talk about in my book, my first book, and you talk about in your book, which was serendipitously discovered, but it was to benefit mankind. They said mankind back then, now you'd say humankind. But this was a medical device, but it was invented by a physicist. Talk about that tradition that you're carrying on so proudly today.
Right, so much of the discovery and innovation in this story actually traces the path through the invention of particle accelerators, which are, the main tools that we have now to explore first inside the atom and then to explore well beyond that and these particles that are out there in the universe. But along the way, as each of these new technologies was invented and new ideas came along of how to pull particles out of the atom, form them into a bunch and give them a lot of energy in a very precise way, that itself became a whole field of physics, which is called accelerator physics, which is the field that I work in. So rather than, although I studied it, I don't daily use, quantum field theory and all of these things.
Yeah.
I'm back there using, mostly advanced electromagnetism, nonlinear dynamics, things like that. And what my role is I'm trying to go back to the drawing board of how it is that we can take these particles and give them energy on some fundamental way, and trying to understand how we can reconfigure particle accelerators to make better use of those particles, and produce better quality beams for all sorts of applications. So my previous work was actually in trying to produce very high intensity beams. Now that's important for particle physics because you just get more collisions if you have higher intensity beams. But it's important in some other areas as well, like neutron generation for neutron spallation source facilities, like big scientific facilities that other people use. And the challenge there is quite interesting, right? Most people don't think about this. You can only accelerate a charged particle with an electric charge, and yet charged things repel each other. And most people don't think about this because they think about, if you picture a beam in a particle accelerator, most people in their mind's eye kind of picture a laser beam, right? Like this organized collection that goes forward. But light's easy because it doesn't push itself apart in the way that a charged particle beam will. So if you try and pack a whole lot of charged particles in there, imagine tiny galaxies as the bunches of particles, rotating, swirling, doing all these crazy nonlinear effects, interacting with each other, interacting with the magnets and the beam pipe. There's electrical and magnetic fields flying around everywhere. There's all sorts of stuff going on, and yet we need to be able to control that while it's going around almost at the speed of light, so that we lose less than one particle in a million, or we risk melting the machine down. Right. So this is incredibly important that we get this right. So
and sometimes there'll be a person in there, too, right? For added difficulty, a human being not too far away.
That's the thing. And then when we get to applications, then you're taking that same physics and you want to get that right, because at the end of that device, you're placing a patient who has a tumor and you're trying to treat that tumor very, very precisely, in multiple forms, both either with heavy particles or with X-rays and radiation. So then it becomes even more important that we understand exactly what's happening with that beam and how to control it. Yet at the same time, there's always this pressure. Everything has to be smaller. Everything has to be cheaper. Everything has to be more effective. And the way that we can do that is going back to the physics drawing board and going, right, how can we change this system such that we can shrink these things down and make them cheaper and better and more purpose-built for the applications that we have. Most people don't realize that there's not just 2 or 3 particle accelerators in the world doing physics stuff. There's like 50,000 particle accelerators in the world, and about half of them are medical and about half of them are industrial, and like a tiny fraction is used for physics.
People here in San Diego or in California generally, they're like, we don't want to build any more nuclear reactors for power, they're dangerous. I'm like, do you realize just in San Diego Bay there's like 6 nuclear reactors and submarines and aircraft like, you don't just like, oh, they turn off when they get to port. No, but of course your technology is used for very peaceful purposes. And I wonder, as happened with people ranging from, the first Nobel laureate, with the discovery of what we now call Röntgen rays. I still wish we called them Röntgen rays. I think it's fun.
They still do in places in some X-ray departments in Germany, right? Are still called röntgenology or Röntgen rays. Yep.
But I think you said that he's the one who gave it that distinction, and then later there were things called N rays, and now we have beta rays and so forth. That was serendipitous, and I wonder, dovetailing back to the question that we were just kind of ruminating on with at the start, which was these larger and larger accelerators, so to speak. I wonder if we're going to come full circle in that my fears will be allayed that we couldn't really maybe have counted on particle physicists to trust, cosmologists, unless there were the discovery of cosmic rays, etc. And we wouldn't have predicted that you could get this device for removing tumors, from a particle, from a cloud chamber, or, from an electroscope. But you proved the pathway, direct lineage and the heritage there. But I wonder, are we going to come full circle where we can no longer build bigger and bigger instruments of the type you talk about the cost? And even though, as you rightfully point out, it's a tiny fraction of the cost that I think Americans spend on lipstick every year is the NSF or NASA's budget. Nevertheless, it's not likely. I mean, past guest James Beecham has talked about putting a collider on the moon. We'll see when, my great-great-great-grandkids are graduate students, maybe that'll happen. What do you see as the future? Do you think we're going to stifle innovation because we will simply have picked all the low-hanging fruit by the successes of the men and women that you talk about in this book? Have we outdone ourselves in that there's really unlikely to be discoveries tantamount to, the CT, MRI, PET technology, all the stuff that you work on and contribute to, or stuff that I contribute to in cosmological experiments, which are also getting big? Have we picked all the low-hanging fruit, or is there hope? Are you more optimistic than pessimistic?
Yeah, my initial response to that is I'm probably more optimistic than pessimistic around it. First of all, with like the large scale experiments, I think I've come to realize that one of the lovely things about the serendipitous way and the sort of slightly unexpected way in which science progresses is that sometimes a kind of left field suggestion will actually end up taking over. And this happens, in my field at least, this has happened again and again to revolutionize the technology with some new idea that's come in. And so let me just give you a hint of one of those is that one of the limitations in and why the accelerators are so big is because you can only accelerate so much using a voltage, right? Because at some point you're going to have electrical breakdown. Well, if you take a system that's already electrically broken down like a plasma and you start generating electric and magnetic fields in that, you're not limited by breakdown anymore. And that's exactly what people are looking at in plasma-based accelerators. So driving that either with a laser or another particle beam to try and create electric wake fields that can accelerate particles. And even in my career, even in the last 10, 15 years, that has come from a almost completely theoretical concept to something where they're now working with industry to make small scale tests of whether or not they can use this for X-ray imaging, depending on the scale of things. So like that development is incredible. And I'm keeping a very close watching eye on that field at the moment, because if that technology gets to the point where I think we can really use it for large-scale accelerators, I will be in there trying to work with them on how you put this stuff together, how you put our existing knowledge together with their crazy plasma stuff, and generate the next generation of machines. And maybe it's something like that allows us to go beyond the energy reach, for example, that a machine the size of the moon would require, and instead build a smaller system by being smarter and by taking the ideas that we know and combining them together. And that's where I have the thing that I often say, that the sort of utility of these ideas really grows over time. So I'm optimistic that we will solve those sorts of challenges and won't have to put all our eggs in one basket and go very, very, very slowly for decades.
Now, I had a visitor come in, not a graduate student, but a young child. So hopefully he's out of earshot range now. But
I could tell something was going on. I was like, "What's going on? Am I over time? Is he?"
We'll make sure we doctor that up. So we've reached the hour when I like to ask my guests who come on a series of questions that I call existential questions. We have time for two. I'm going to ask you first, though, pertinent to the name of this podcast, which is called Into the Impossible, based on Sir Arthur C. Clarke's famous saying that the only way to discover the limits of the possible is to go beyond them into the impossible. And in this book, you talk about persistence. And I wonder if you could elaborate, perhaps as a way to answer this question of what gave you the courage to go into the impossible. You mentioned not only persistence, but the freedom to persist. What does that mean? Can you elaborate on what do you mean by the freedom to persist, not just the trait of being persistent?
Yeah, so I see the trait of being persistent or resilient as more an individualist approach, right? Whereby, I'm struggling through something and you're like, just keep going. And I, come into work every day and continue working on it. I think that's very different from what I'm trying to get at, which is the freedom to persist is more a cultural phenomenon, where it's like, are we creating environments in which people can actually persist without having to give up all the time? And this, in some other occasion could lead to us really analysing the structure of how we do research and how academia works in particular. We always have all of these different pressures on us, now more so than in 100 years ago. The stories that I've told in the book, because most of the men had wives at home, they were free to just sort of do their thing. Their experiments didn't cost much, so the funding was available, and they could just basically sit and think and work and do all of that. Now, oh my goodness, the role of an academic, we have like 17 different jobs in one when we do research. And then we're constantly having to find funding to keep our research going. And that is such a killer for creativity and curiosity. It means that we're much less likely to take risks with our research, and we're much less likely to follow our curiosity, because we're like, oh, that little thing that's happening over there in my experiment that I don't understand, oh, I'll just assume it's not important. Whereas it might have actually been the discovery of something completely new if you depending on obviously the scale of experiment that you do. So to me, the freedom to persist is quite an important one, because it's about giving the people the opportunity to actually pursue the goals that they're looking at. And that's a real shift in perspective societally as well, in how we value research and how we value this activity, which seems on the surface to not day to day produce something which has monetary capitalistic value, right? And even though in the long term, as I've shown in the book, it might have, it also might not have. And we still need to value it, even if it doesn't produce capitalistic outcome. Maybe this 100-year period is the period that had the great capitalistic outcome. And from here on out, particle physics is not going to produce anything that someone can monetize. We should not stop it, even if that's the case, because we are humans who want to know things, and and making sure that we give people the capacity, the time, the resources, the space to actually pursue those questions kind of on behalf of humanity. That sounds very grand.
No, it's
but
true.
Giving people that capacity is such an important thing. And if we hadn't done that
if you
previously...
ever feel, I mean, if you ever feel, kind of shy about, extolling the virtues of experimental research and basic research, because maybe it's not monetizable. I mean, think about Dirac, or Hamilton. Somebody says, "Oh, what use are these spinners? What use are these, quaternions?" He said, well, someday they'll describe antimatter, which will then be used to make positron emission tomography. It's like you could never ever predict it, right?
Right, and famously, it's like what use was electricity, right? Even back in the day, and the experimenter says, "Oh, I'm not sure, but one day you'll tax it." Well, exactly. And I think that's the thing. Right. We're so limited in how we can imagine the future use of these ideas that are coming out. And that is really the nub of the story I've tried to tell, is stop limiting ourselves to go, oh, well, what use is that going to be when you want the result in 3 years in a small grant from the government, right? No. The use might take decades. It might take centuries, but the knowledge is what's important.
Right. And what use is a discovery that never comes about because you were so gung-ho about monetizing it, and it's very short-sighted. So Professor Sheehy, last question that I like to ask guests also comes from Sir Arthur C. Clarke, where he said, when an elderly but distinguished scientist says something is possible, she is almost certainly right. But when she says something is impossible, she is very likely wrong. I want to ask you, what have you changed your mind about? What have you been wrong about? Or what have you been maybe misdirected about and later found to be completely surprised or serendipitously so? What have you been wrong about, if anything?
Oh, that's a really good question. I think actually, what I was wrong about was whether or not I could be a physicist. This is quite a personal answer to that question, I think.
Yeah, no, please. And I'm sorry, I didn't mean to imply that you're elderly. I just meant to imply you're distinguished. Go ahead.
I can take it. So as you said before, like obviously to get to the point that as a fully fledged academic running a group, and sort of having that permanent academic position was always something that I thought, well, I'm in this for the research, and if that career doesn't work out, that's fine by me. It may never work out. Statistically, it's unlikely to work out. But I also underestimated my own ability, I think, to do research, partly because of the factors we were talking about earlier about it's so dependent on things like persistence and asking good questions, rather than just about whether or not you can solve a mathematical problem faster than your peers, right? So we're given this wrong impression in the early years of our training. And the other aspect of it for me was very much that I felt somehow different often to the people around me. The primary one was gender, but often it was just because I have these many different interests in the world, including things like wanting to contribute to something which helps society, as well as wanting to contribute to the fundamental questions in the world. And so I guess for a long time I was under the impression that, like, okay, well, I'll just do some research for other people and then eventually I'll probably go on and work for a company, or maybe I'll do science communication and write books. I end up doing both, I suppose. And so that's the thing that I was wrong about. And that was one of the lovely things in writing this book and finding the stories of all the other women who went before me, was just realizing that, and even a lot of the men, they all had that very similar experience. Most of them felt like for most of their career that they were failing.
Right.
And being able to sit with that, move through that, persist, do research anyway, and come out and go, oh, actually, if they can do it, and they all won Nobel Prizes, all the people I'm writing about, I'm like, well, I'm not going to win a Nobel Prize, but, maybe I can do this after all. So, yeah.
It's such a delight, and it's a gift to young minds, and I think that's the surest test if you've succeeded is how much would you have paid for this book when you were a young student? And I think that's the truest test, and I expect for you as it is for me, this is a wonderful book, and it's a much needed book. As I say, I love my theorist friends. I've had on more than almost anybody from all walks of theory. And even I've had on economists, but there's something to be said for those of us that are confronting the cold hard reality, not just as you say of understanding the logic and the mechanisms that we're searching for, but also the budgets, the persuasion, the confidence that it takes to get to a point as you have surely gotten to, and will continue to do so. And I can't wait to see what you come up with next, Suzie. It's been a delight to talk to you. Congratulations. This is
Thanks,
a smashing success. And it is a book to be savored, so please do pick up copies, either digital, audio, or printed, as I have consumed in all those formats. I can attest to them. Suzie, thank you so much.
Thank you. Lovely to nerd out with you for a bit.
Yes, and we'll nerd out again, hopefully in person someday.